So thank you. It's great to have such a exciting meeting and be able to participate in it. I'm sorry I wasn't here earlier, but it's great to see so many people, many of whom have contributed to what I'd like to talk about. So in particular, I'm going to report on some joint work that's already been mentioned. So this is with Ronan McMullen and Alex Wright. And part of it, and then another part is with the same authors plus Eskin, Alex Eskin. Okay, but let me start with a little preliminary. So I want to describe some new developments in the theory of billiards, and actually we've had a perfect introduction to what I want to talk about with the course that Dawei gave, and we already have cone manifolds on the table and complex hyperbolic space. So let me start with an analogy that is pervasive in the subject of dynamics on moduli space. It's so pervasive that people don't even talk about it. So let me talk about it, since this is a summer school. It's a kind of a dictionary. It's an imperfect dictionary. The translations are not quite correct, but it's very suggestive. So on the one hand, we have the moduli space of Riemann surfaces of genus G, which is the quotient of Teichmuller space by the action of the mapping class group. And the idea is that this space is somehow analogous to more traditional homogeneous spaces or symmetric spaces. So since this is a complex manifold, you might compare it to the quotient of complex hyperbolic space of some dimension n by the action of a, say, cofinite volume group of isometries, by a lattice in its isometry group. And maybe I'll just call this M. Now on both sides, we presented these objects via some sort of uniformization theorem. We've described their universal coverings. One thing that's remarkable is that these are both varieties, algebraic varieties, in the sense Dawei already discussed. There's some similarities between them. So how should you picture complex hyperbolic space? Well, in fact, complex hyperbolic space is the same as the ball. As a complex manifold, it's the same as the unit ball sitting inside of Cn. And it turns out that Teichmuller space is similarly a bounded domain in a complex affine space of dimension 3g minus 3, at least when g is greater than or equal to 2. But it doesn't look like this. It's, I don't have a picture with me, but it looks like this. And in fact, if you look close to the boundary, you see something that looks to first order like this. It has these sort of cusps on the boundary. This is if you take a slice with the complex line. And then these cusps actually are decorated. So there's another little cusp here, and then there's cusps here. These are enumerated by the rational numbers 1 over n, and they come up closer and closer like this. And then each of these things has little cusps decorating it, getting smaller, and so on. And one reason I draw it at that level of detail is that this space is very far from being convex. It, in fact, it's not even star-like from any point. If you shine light here, you can't see, or say from infinity, the light gets stuck on these cusps. It can't get inside and on everything. And that's one of the huge differences. But before we talk about that, let me say that again that on both sides you have something called the Kobayashi metric. And I won't say exactly what this is, but in Teichmuller space, it's equal to the traditional Teichmuller metric. And in the ball, well, the ball is a homogeneous space. So any point in the ball is equivalent to the origin under a complex automorphism. And if you want to know the distance to some other point in this metric, you just take the complex line that they span. And its intersection with the ball is a copy of the unit disk. And the unit disk has a hyperbolic metric on it, and you use that metric to measure distance. That's what's called the Kobayashi metric. And these disks are isometrically embedded for the Kobayashi metric. They are what are called complex geodesics. So there are, I'll call it the upper half plane, although it's isomorphic to the unit disk. This means with its metric of constant curvature, and it turns out the right normalization is curvature minus 4, maps in holomorphically and isometrically to give you what's called complex geodesic. So the hyperbolic geodesics here go over to geodesics for the Kobayashi metric here, but in fact the whole disk goes in isometrically. And these are all of the isometrically embedded disks. Every other disk mapped into complex hyperbolic space contracts from the hyperbolic metric here to the Kobayashi metric here. That's a sort of a Schwarz lemma. Now Teichmüller space amazingly has the same property. Namely, through every point, there exists what's called a Teichmüller disk, or and again, it's an isometric and holomorphic image of the upper half plane. So in that way, again, there's some striking similarities between these two spaces. So here, again, there are complex geodesics through every point and in every direction, making it look rather homogeneous. OK, so just to indicate a little bit about how we are really still in the age of discovery regarding Teichmüller theory, there's a second metric you can define on any complex manifold. This metric is defined by requiring the Schwarz lemma holds for maps from the hyperbolic plane to the manifold, or from the unit disk to the manifold. You can ask, however, for a metric that satisfies the Schwarz lemma going from the manifold to a disk. So you consider all holomorphic maps from the manifold to the unit disk in the complex plane and build a metric canonically out of those. That's called the Carathodory metric. And in the case of the complex hyperbolic ball, or in fact any bounded symmetric domain, those two metrics agree. And they agree for the simple reason that if you have a holomorphic disk through the origin, then you can just project orthogonally back to the unit disk. And the composition of those maps is an isometry. Each is distance decreasing, so in fact, they have to both be isometries. So on this side, Carathodory and Kobayashi agree, Carathodory metric. Whereas on this side, fairly recently, Vlad Markovich proved the long-standing conjecture that the Kobayashi metric is not equal to the Carathodory metric for Teichmüller space. So there is some failure of this dictionary to really work in all detail. Perhaps even more interesting, if you look at the ball of radius r around the origin in the Kobayashi metric here, it's just a ball of a different radius. That's also true for any bounded symmetric domain. The balls of a given radius are just rescalings of the outer ball. In particular, all of the metric balls are convex. So there's a beautiful new theorem here as well. I should have said this was Markovits due to Bork and Rafi after some preliminary work with Lenzen as well. I think the main idea is in Rafi and Lenzen, which says that in Teichmüller space, balls need not be convex. It's tempting to think of Teichmuller space as being negatively curved, or at least non-positively curved. But in fact, there exist balls of unit radius around a given, of a large radius around a given point, which are not geodesically convex for this metric. As I was preparing this talk, I was thinking how surprising that was, and then I realized that in fact it's not surprising at all, because you sort of expect, by analogy with the complex hyperbolic case, that a very large ball will somehow look like something that sort of feels the boundary here. And since the boundary is very far from being convex, maybe at least that's some intuition as why the balls need not be convex either. Anyway, that's a recently settled problem regarding the geometry of Teichmuller space. Okay, now let's get to dynamics. I know it's a bit early to be changing blackboards, but I want to work vertically. Sorry?
In that picture, the parts according to the single growth curves are where?
You waited till I put it up 6 feet, right? They're there. Sorry. So this is Teichmuller space. It's the universal cover of moduli space, and if it were just the upper half plane, the thin parts would be horocycles resting on the rational numbers. And what's happening here is each rational number is turned into a cusp. And so these horocycles are replaced with sort of cardioid-like looking regions that sit on top of each cusp. That's roughly what the thin parts look like. Other questions? Okay, so let's go to dynamics and homogeneous spaces. So a big a mathematical reservoir that one can draw on in the study of objects like complex hyperbolic space is the fact that complex hyperbolic space itself can be thought of as the quotient of a Lie group by the action of its compact subgroup. In fact, this Lie group is just SU1n, as was mentioned in Irena's talk. And so we can think of M as being G mod K mod gamma, and then there's this homogeneous space G mod gamma, which sits over M. And this is essentially the frame bundle, the unit frame bundle F of M. So you might hope for something like that in the case of Teichmuller space, but Teichmuller space, it turns out, is not a homogeneous domain. Its entire group of automorphisms is the mapping class group. Nevertheless, we can try. And so what you can try, which is a little bit odd, is you replace this Lie group here with the bundle QTG. This is the Q1TG. This is the bundle consisting of a Riemann surface plus a quadratic differential, holomorphic quadratic differential on the Riemann surface, such that the total area of that differential is equal to 1. And this turns out to be the unit cotangent bundle, the Teichmuller space. So that sits over TG. And now, if this were a group, then we could act on it on this side and get something interesting going on in the same way we can act on G on this side and get the horocycle flow, the geodesic flow, all sorts of dynamics on this bundle over M. And here, as you know well, the analog is there's an action of SL2R in both cases. SL2R acts on the space of quadratic differentials by thinking of them as flat structures and adjusting how they relate to R2. And SL2R also acts on the frame bundle of this complex manifold in such a way that the diagonal group acts by the geodesic flow. So we do have those actions in both cases, and we can try to study them dynamically. Now in this setting, there's a beautiful theorem of Marina-Ratner, which tells us that the closure of every SL2R orbit is geometric. And one consequence of that is that if you take a map, one of these complex geodesics, and you map it to M, well, that turns out to be just the projection of an SL2R orbit in the frame bundle back down to M. And the theorem is that the closure of that complex geodesic is a algebraic subvariety of M. And here, of course, we have the beautiful result of Esken, Mirzakhani, Mohammadi, and then supplemented by the result of Simeon Philippe, that says if we have a complex geodesic in a moduli space, then the closure of this complex geodesic is also an algebraic subvariety of moduli space. It's not some strange fractal object as it might otherwise potentially be. So one often says Ratner holds for moduli space. Okay, but Marina-Ratner's theorem doesn't just apply to groups like SL2R. It applies to any group that's generated by unipotent elements. In particular, it applies to the unipotent subgroup here of upper triangular matrices. And it says that the closures of the orbits of this horocycle flow generated by N in the frame bundle of M are also always submanifolds of a homogeneous, easily understood type. And so you might also ask, not what can you say about the closure of these complex geodesics, but what can you say about the unipotent orbits in the space of quadratic differentials? And it's now known that Ratner's theorem also does not hold for moduli space. So it holds for SL2R, but Chaika, Smiley, and Weiss recently proved that it does not hold, even in the case of genus 2, for the action of N. So again, we're seeing some imperfection in this dictionary, and there's some tension here, which is probably what makes the whole subject so rich and interesting. Okay, now let me come to the main subject of my talk, which is totally geodesic varieties. So you have a space where you have a notion of geodesic. What does it mean for a submanifold to be totally geodesic? It means that whenever you take 2 points in it, the geodesic joining them is also in that set. So it's convex in the geodesic sense. So you can ask, for example, in this complex hyperbolic space, do I have any totally geodesic subvarieties of M? And the answer is good in the case where gamma is arithmetic. And indeed, when gamma is arithmetic, then this implies that if you take complex hyperbolic space and you take its intersection with a subspace defined over a suitable number field, so some finite extension of Q that's related to the arithmetic of the underlying lattice, then first, the intersection of S, let's say this is k-dimensional, with complex hyperbolic space is again a complex hyperbolic space of lower dimension. And moreover, the stabilizer of this space inside of our big lattice acts with finite volume quotient on Sk. And so you get, so to speak, a map from Sk to some smaller dimensional variety Tk sitting inside of Mn. And this variety is totally geodesic. So in the arithmetic case, there are totally geodesic varieties all over the place, densely inside of the manifold, and of any dimension you want. Now, what about Teichmuller space? We can try to look for subvarieties of Mg, which are totally geodesic with respect to the Teichmuller metric. Now, what I want to emphasize is that this statement, that the closure of a complex geodesic is a variety. This does not guarantee that this variety itself is totally geodesic. The fact that it's a closure of a geodesic only tells you that certain points on a one-dimensional locus are connected by the corresponding geodesics, not that two arbitrary points in this closure have their geodesic. And in fact, there are many instances of closures of complex geodesics which are not totally geodesic inside of moduli space. In fact, there were until recently the only known examples of totally geodesic varieties in moduli space were the Teichmüller curves, which have already appeared, I think, in several cases. So here's my first motivating topic. My motivation is the following: can we describe the totally geodesic subvarieties phi contained in Mg? And I'm going to add an n here as well. Often it will be important to allow these Riemann surfaces to have punctures. So one thing I'd like to point out is that there are many hard questions in this field. One of the hardest and most provocative one is to describe all of these possible orbit closures here, or all of the SL2R invariant subvarieties of the cotangent bundle. Those have been mentioned already. By the way, where would those come from? They should come from subgroups of G. You see, the whole conundrum is that this is not a group. So where are these subvarieties ever going to come from? Maybe they shouldn't be there at all. So it's hard to find those gadgets. But this is easier than finding the SL2R invariant subvarieties. All of these will give SL2R invariant subvarieties, but the converse is not at all the case. This is a more rigid setting. Yeah.
In the homogeneous case, is it true that all the orbit closures are for the SL2R actually are totally geodesic?
Yes, it is. That's special to this Lie group in geometry. No, in general. So that was proved in the case of real hyperbolic space by Nimesh Shah, and I think it follows in this case by the same type of argument. Are there other questions? Alex can contradict me if you think it's okay. Yeah. Question?
Why do you look for the Teichmüller metric? Why is it more natural to look at geodesics for the Teichmüller metric?
So the reason I'm looking for geodesics for the Teichmüller metric, well, there's several, but one is that they correspond exactly to the SL2R action on the tangent bundle. So if you want to study billiards or flat structures on surfaces, this is the natural metric to use. But I'm not even really emphasizing its metric geometry. And in fact, we'll have a way to talk about SL2R invariant subvarieties shortly that won't even make reference to any metric. Did you have another metric in mind?
I don't know, the fact that it didn't work for the subgroup N.
Yeah.
Maybe meant that if we look for another metric, then I don't know, one which is more compatible with the complex.
Yeah. So this is, as far as I know, the only metric that's naturally built out of the complex structure, except that would be a slight lie because the Kobayashi metric is also built out of the complex structure. But we're really capitalizing on the fact that when you look at these SL2R orbits, these closures have a sort of double life. You can think of them in terms of flat surfaces, and there this SL2R action is elementary, or you can think of them as algebraic subvarieties of moduli space, and then you don't see the SL2R action at all, but somehow some beautiful algebraic properties of this locus emerge. And I think what we're really seeing in Teichmüller theory today is that this interplay between algebraic geometry and homogeneous dynamics is richer than it was thought before. And I'll try to just give an instance of that. Other questions? OK. So let me just say a little bit, not at all complete, about what's known about the totally geodesic subvarieties. So the first examples are where the dimension of V is equal to 1. These are called Teichmüller curves. And I should say, I'm going to move back and forth between the space of quadratic differentials over moduli space and the space of holomorphic one forms. They're very closely related, and there are double covering tricks to pass between them. But I really need to use both. In any case, the Teichmüller curves provide the first interesting examples of subvarieties of moduli space that are isometrically embedded. And they correspond to closed SL2R orbits, usually described in terms of the space of holomorphic one forms over moduli space, which I'll denote like this. So SL2R also acts here. Almost every orbit is dense, but occasionally you find a very small orbit which is closed, and it projects to give this complex geodesic, which is just covers an algebraic curve sitting inside of moduli space. Now, I should say there are some totally geodesic submanifolds of MH which are of high dimension but are kind of trivial. Namely, if you take a Riemann surface of genus 5 and choose a covering, say an unramified covering of genus 12, then to every complex structure of genus 5, you get a new complex structure of genus 12. And that gives a map from M5, or rather a finite cover of M5, into M12. And it turns out that the image is totally geodesic. But you're just sort of inheriting the theory of lower dimensional Teichmüller spaces. So the varieties that arise in that way are said to be imprimitive. They're really coming from lower dimensional moduli spaces. And so when we talk about these totally geodesic varieties, we really want them to be primitive. That is, they do not arise from a covering construction. OK, so the first interesting examples, the first primitive ones, were these Teichmüller curves discovered by Bill Veach. And a typical one is the following. Let me describe it to you very concretely. So you take two copies of the regular pentagon, maybe make the vertices lie on the real axis at 0 and 1, and then this central vertex is up wherever it has to be at IY. And now if you're given any other point in the upper half plane, you associate to that point the image of this picture under a real linear map. So you keep 0 and 1 where they are, and then if you pick a point tau in the upper half plane, you make that the top of your pentagon, and make it the top of the pentagon below. And in that way, every point in the upper half plane determines a pentagon, a pair of pentagons. And now if you identify opposite sides, you get a Riemann surface of genus 2. And the map that sends tau in the upper half plane to this Riemann surface of genus 2, let me call that F, is in fact a complex geodesic. And its image in moduli space turns out to be an algebraic curve. So those were the first examples due to Bill Veach. And since then, a handful of other series of Teichmüller curves have been discovered. So let me just quickly say a little bit about what's been done. So one of the modern developments is that we've come to realize that if you're looking for Teichmüller curves in moduli space, your first inclination might be, well, these curves should have some sort of special symmetries. So maybe I should look in that part of moduli space. But that's not right. The internal symmetries of a Riemann surface are always destroyed by the action of SL2R. But what is sometimes preserved are not automorphisms of the Riemann surface, but endomorphisms of the Jacobian of the Riemann surface. And therefore, one should look for Riemann surfaces whose Jacobians have special endomorphism rings rather than for Riemann surfaces with special automorphisms. And with that in mind, we now know, as of 2000 something, that in addition to these Veitch examples, which work for an arbitrary n-gon, there is also an infinite sequence of Teichmüller curves contained in the moduli space of Riemann surfaces of genus 2. And these can be described as the set of Riemann surfaces such that the Jacobian of x admits real multiplication by some real quadratic order of discriminant t with an eigenform that's going to give the flat structure omega, and this eigenform should have a double zero. That turns out to define an algebraic curve, possibly reducible in M2. And then there's a long story about trying to find the number of components of this curve. It turns out there's only one or two components. And the next step in the development is that there's a generalization of this construction in which Jacobians are replaced with what are called Prim varieties. And I won't say this in detail, but allows you to make similar constructions in genus 3 and 4. And so in each of the genera 2, 3, and 4, there are infinite sequences of primitive Teichmüller curves. And I should say the theory of this, these prim, the classification of these prim things is quite difficult. And this was carried out by Erwan and Nguyen. And I should also say that before the 21st century, after Veitch discovered the regular n-gons generate Teichmüller curves, there was a related discovery by Ward. And to say what his discovery is, let me rephrase what Veitch proved. So what Veitch proved is the following. I want to associate to a pentagon I want to associate to it not this strange 8-sided figure, but just a triangle. So where's a triangle that's naturally attached to this pentagon? Well, let me take the centers of these two adjacent pentagons, join them by an edge, and then join that by edges to a vertex. So there's a triangle, and it has the property that if you unfold this triangle and use it to try to create a one form, that is, try to reduce the theory of billiards in this triangle to the theory of a one form on a Riemann surface, you will find that it unfolds to give exactly the same Riemann surface as the pentagon. So the pentagon really comes from, is sort of equivalently described by studying a triangle where the internal angles are proportional to 1, 1, and 3. The important point being that they add up to 5. And this construction works with 3 replaced by any integer to give Teichmüller curves of varying genera. So about 10 years after Veitch made this discovery, Ward proved that there's another infinite sequence of triangles with internal angles 2, 1, and let me call it m minus 3, which generate another infinite sequence of Teichmüller curves, but of genus going to infinity. So you see what we're seeing here are two different types of constructions. I call these horizontal because you vary this integer d through infinitely many values and you get an infinite sequence of Teichmüller curves in a fixed moduli space. This sequence I call vertical because the genus, which depends on this integer m, goes to infinity as m goes to infinity. And then Bow and Muller discovered a beautiful generalization of the Veitch and Ward examples, which also gives now several systems of Teichmüller curves, but again vertically with genus going to infinity. So these Ward and Veitch examples are now subsumed in what most people call the Bow-Muller series. And in fact, up to a couple of years ago, maybe apart from one or two exceptional triangles, these were all the known examples of Teichmüller curves in moduli space. Now, I should say briefly, for those of you who are interested in more elementary dynamics, Veitch's motivation for proving that this object is a Teichmuller curve is to show that billiards in the pentagon has optimal dynamics. Every billiard trajectory in a regular n-gon is either periodic or it's uniformly distributed. That's a very striking dichotomy that doesn't hold for many other pentagons. So it's very hard to verify in any given rational polygon, let alone an irrational polygon. So every time you discover a Teichmuller curve, you might look hard to see if you've also discovered a new optimal billiard table. That's a slightly different, but the two types of objects are closely related. Okay, now, so there's maybe 30 years of development of the theory of Teichmuller curves. There are no totally geodesic surfaces. I can explain why there are no totally geodesic surfaces. They really shouldn't exist. The reason is that if you look at the Kobayashi metric in a homogeneous space, like complex hyperbolic space, the unit ball in the Kobayashi metric is a round ball. The Kobayashi metric turns out to be a Riemannian metric, a Hermitian metric, a Kähler metric, in fact, on complex hyperbolic space. So here, K, Kobayashi, is equal to K, Kähler. What happens in the case of Teichmuller space? It turns out the Teichmuller metric is not even given by an inner product. Its unit ball is some strange convex body. It's symmetric. It has all sorts of bends. The boundary is not very smooth. The lack of smoothness of the boundary can be used to show that the automorphism group of Teichmuller space is very small. And to have a totally geodesic subvariety of dimension 2 or more, you would have to be able to find a slice of this ball with some very unusual properties. It would have to sort of behave well with respect to both projection and inclusion into the ball. So one can, in fact, make an argument that there are no totally geodesic surfaces in moduli space, a heuristic argument based on the fact that these balls are very regular. And thus, it came as some surprise, and I'm very glad to have been able to participate in this story, that a few years ago, I guess this is 2016, Ronan Mukamel, Alex Wright, and I proved that there exists a totally geodesic surface, and by which I mean complex surface, F, contained in M13. So this surface just consists of families of elliptic curves with 3 distinguished points on them. And in fact, every elliptic curve arises. So to describe this surface, I would just have to tell you which specials of triples of points on an elliptic curve are special. And I won't do that, but let's just say it has to do with algebraic geometry from the 1860s. There are some curves called the Hessian and the Kählian and the Hippian and the Quiffian, all associated canonically to a cubic curve. And in terms of those and polar curves and dual curves, you can describe this surface in terms of algebraic geometry. OK, so we wondered for some time whether or not there was this was sort of an isolated example, or if it could be put into a broader context. And that's what I want to present today. So amazingly, this work with these co-authors does the following. We take the Veitch and Ward study, and we make the next step. We study quadrilaterals instead of triangles. OK, so to describe the results, let me just introduce some notation. So let me just say what I'm going to do. My goal is to describe a suite of 6 quadrilaterals leading to 3 totally geodesic surfaces, 6 SL2R invariant subvarieties of the space of 1 forms, 2 series of Teichmuller curves, and 2 new series of optimal billiard tables. And the flex surface, which we previously approached from the point of view of algebraic geometry, will occur as one of these 3 surfaces. OK, so here's the language I'd like to use. I've already introduced it informally. Let me just make it slightly more formal. So I want to discuss polygons, where I've just specified the angles of the polygon. So this is very similar to specifying a cone type, what I'm about to say. So a polygon type will just be a set of integers, a1 up to an, positive integers, with the property that the sum of the ai's is n minus 2 times m, some integer m, and the GCD of a1 up to an and m should be equal to 1. And this polygon type, this sequence of integers, is used to specify polygons with internal angles, theta I, which is just pi times ai over m. OK, so this will, of course, be an n-gon. And one example, which will be important for us, is the case 1, 1, 1, 9. So here m is equal to 6. And the polygon looks roughly like the logo of the Star Trek Federation. So it has 3 angles, which are each of 30 degrees. These small angles are 30 degrees. And then here, there's a total angle of 207 degrees around that last obtuse vertex. Now notice that quadrilaterals, unlike triangles, they come in different shapes, even up to similarity. There's a 1-parameter family of polygons of this type, whereas there's a unique triangle of a given type. And these polygons are closely related to certain metrics on the sphere. Namely, you could take this polygon with its flat metric and just double it. And it would give an example of a cone metric of the type discussed in Irena's talk, although the angles would not all be of the right type to fit into that discussion. OK, so now once you have a polygon type, you can associate to this, and we call this polygon type for brevity A, you can associate to this a space of cyclic forms contained in the moduli space of holomorphic 1 forms of a given genus. So these are, call these the cyclic forms of type A. And formally, they can be described as follows. The space of cyclic forms consists of the set of all pairs, x and omega, where the Riemann surface x can be presented as an m-fold covering of the complex plane defined by, branched over n points. So defined by an equation like this, x minus bi to the m minus ai is equal to y to the m. So that's an equation in the projective plane when you complete it, or it presents a curve which is an m-fold cover of P1 branched over these points, where B1 up to Bn are arbitrary distinct points in the complex plane. That's x. And then once you've written down this equation for x, the corresponding 1 form is given by dx over y. OK, so why are these called cyclic forms? They're called cyclic forms because there's an obvious action of z mod m on this Riemann surface. Multiply y by an mth root of unity. So there's an action of z mod m by automorphisms, given just by r of xy is x zeta m times y, where zeta m is e to the 2 pi I over m. And this has the property that omega is an eigenform for this action. I've used the expression eigenform before. It just means when you pull back this form by the rotation, you get the form multiplied by a constant, which turns out to be the inverse of the primitive mth root of unity. Okay? So these surfaces all sit over the projective line by just taking the x coordinate with det group z mod m. And the genus of x, by the way, which I'll just denote by g, can be computed by, actually, the negative Euler characteristic is easier to write the formula for. 2g minus 2 is equal to the sum of ai minus the GCD of ai and m. OK, so let's do an example. In the case 1119, the GCD of 6 and 1 is 1. And the GCD of 6 and 9 is 3. So I get 9 minus 3, which is 6. So 6 is equal to 2g minus 2. And so g is equal to 4. OK, so how to think about these families of cyclic forms? Well, if you just take this formula I wrote down for omega, that is, take the mth root of this side of the equation, omega is a multi-valued function on the Riemann sphere, but the absolute value of omega is not. And what does the Riemann surface P1 look like with respect to the form, the absolute value of omega? Well, if these branch points are on the real line, then it just looks like the double of one of these polygons. So what we've done really is we've taken the cone metric on the sphere, we've defined it in terms of a certain differential form, but that form is multi-valued, and then the cyclic form is just the Riemann surface plus form where that metric becomes single-valued. OK, so that's the definition of the space of cyclic forms. And the cyclic forms provide us with a very convenient way to describe loci inside of the moduli space of one forms. Whenever you have a subset of the space of one forms, you can see what it generates under the action of SL2R. That is, you can take the SL2R orbits and take their closure and say that's the variety generated by these forms. So I'm going to let omega GA be equal to the closure of SL2R applied to the space of cyclic forms. Just take the closure in the space of all one forms of genus G. And by these deep results that we've quoted, this is, in fact, an algebraic variety. And the theorem is that for the following 6 values of A, the locus omega GA is let me say, an irreducible, unirational, SL2R invariant. It's obviously SL2R invariant by definition. Subvariety of omega mg of complex dimension equal to 4. And moreover, this variety is primitive in the sense that it doesn't arise from any previously known examples in lower genus by a pullback argument, nor does it coincide with a stratum of quadratic differentials or of one forms. OK, now what are the special values of A? Well, one of them is 1119. Another is 1117. 1128. Let's see. 1, 1, 2, 12. 1, 2, 2, 15. And I missed one here. Sorry, let me put that next. 1, 1, 2, 11. 1, 2, 2, 11, and 1, 1, 2, 2, 15. Okay. So in brief, these 3 examples here, well, this example is very special. This corresponds to m equals 5. These 2 examples correspond to m equals 6. These correspond to m equals 8, and this corresponds to m equals 10. And the first 4 examples have genus 4. This has genus 5, and the last one has genus 6. Okay, so that's the first theorem. It says that we can, in the spirit of Veach and Ward, we can describe 6 new invariant subvarieties of the moduli space of 1 forms by just saying the quadrilaterals that generate them. However, in the course of the proof, we actually describe what these subvarieties are. And in fact, I don't have any clue as to how to do the proof without explicitly saying what these subvarieties correspond to. So the second theorem is that in fact, in these 6 cases, omega GA is equal to the closure of the space of dihedral forms of type Mn. And so is the closure of the variety of dihedral forms of type M. So remember, M is 1/2 the sum of the AIs in the case of 4 of these AIs. And this invariant N is a combinatorial invariant that can be described by taking the sum of the first 3 numbers here, these small numbers that are always either 1 or 2. So this number N, for example, is always between 3 and 5. Between 3 and 5. OK, so we can say exactly what these new orbit closures are. Now, I don't even have time to define the space of dihedral forms, but I can give you the idea of how this all works in just a couple of pictures. So here's how it works. Let's suppose we start with a cyclic form. So we have this Riemann surface X, and we can form the product of X with itself. Now remember, this Riemann surface can be rotated, and an automorphism of a Riemann surface has a graph. The graph of R is the set of pairs, X, Rx. So we can draw the graph of the rotation R, and we can also draw the graph of the rotation R inverse. And that gives us some subvariety of the product of X with itself. What happens when we go to the dihedral forms? So what the amazing thing is, and this is some amazing coincidence of unexpectedly large dimensions, something just happening to work out for these specific numbers. What's amazing is SL2R, as I've emphasized already, destroys the automorphism group of these cyclic surfaces. They lose their Z mod M symmetry. But what happens to this variety here? Well, since they lose the symmetry R, you can't expect either of these graphs to persist individually. But it turns out that the union of these 2 graphs persists as a subvariety of the product. And these places where it crosses just become resolved into smooth points of a curve or an algebraic correspondence sitting inside of the product X. And this algebraic correspondence has the property that it acts on the space of 1 forms. Because if you have a 1 form on X, you can pull it back to this curve and then push it forward to the other factor of X. This is a standard way to write down endomorphisms of the Jacobian of X explicitly in terms of algebraic maps. And it turns out that T star of omega is equal to zeta M plus zeta M inverse of omega. So in other words, we lose the automorphism and we lose the property of being an eigenform for R, but this algebraic correspondence, this self-adjoint map on the Jacobian persists, and we get an eigenvalue. This omega remains an eigenform for real multiplication as opposed to for complex multiplication. So this is really the miracle, is that this algebraic cycle persists in the product of x with itself. Now, why do we call these dihedral forms? Well, if I give a name to this curve here that results from desingularizing the two graphs, this curve admits a 2-to-1 map to x. But it also has lots of automorphisms. For example, you can flip the two factors in this product structure. That turns out to leave the curve invariant. Those transformations altogether turn out to generate an action of the dihedral group of order 2m on y. And the quotient of this by the action of the flip, that is an element of order 2 in the dihedral group, is our original Riemann surface x. So our original Riemann surface still sits with degree m over p1. It no longer admits symmetries itself, but it is it gives an irregular cover of p1 whose normalization is this dihedral cover of p1. Let me say the same thing once more, even more naively. So we have an action of z mod m on x. Well, I want to make an action of the dihedral group on x. So I know how to rotate the individual copies of x, but what should I do with the flip? Well, I just make f, the element of order 2 in the dihedral group, interchange the two copies of x in such a way that r is conjugated to r inverse. And that gives an action of the dihedral group on two copies of x. And then what happens is that as you start to deform x, these two copies join together to become an irreducible Riemann surface y. The points of x sort of are opened up, and you get a Riemann surface of much higher genus, and it still admits x as the quotient by f. OK, so yes?
So is this, the dihedral group order 2m, is that the same that you get from the unfolding procedure in the table?
No, so the unfolding procedure in the table gives you the cyclic group, z mod m. It does not give you the dihedral group. Oh, you mean if you include this orientation reversing map? Yeah, I think that's right, but that's an accident. You see, that orientation reversing map is only available when these branch points are on the real axis. When these are off the real axis, the cyclic form does not have an orientation reversing symmetry. It's kind of an accident that they coincide. This action, the dihedral group, is by holomorphic transformations, and that reflection is anti-holomorphic. OK, so just tried to say one or two more comments, and to fulfill my promises at the beginning. So I mentioned that there's a way to use real multiplication by certain discriminants to produce Teichmüller curves, and it turns out that these varieties GA can be used to produce Teichmüller curves as well, optimal billiards, and so on. So maybe I'll just state a couple of theorems. So the first theorem is that when m is equal to 2n, GA maps to some surface Fn, which is included totally geodesically in some MHn. And it turns out that the surface, so those are these cases. This is the case 6.3. This is the case 8.4. And this is the last one is the case 10.5. And we get the original flex surface M13 here, a new surface M14 here, and a beautiful surface in M21 that was discovered in a completely different way by Alex Wright and ultimately verified by Ronan McMullen and Abhinav Kumar, and also Paula Pisa has worked on this beautiful surface as well. Anyway, these are the promised 3 examples of totally geodesic surfaces when m is equal to 6, we get an infinite sequence of Teichmuller curves. Let's call them GAD, sitting inside of MG, indexed by a discriminant D, very similar to the case of genus 2. And the reason m is 6 is special is that when m is 6 is special, this is a sixth root of unity, and the sum of the sixth root of unity plus its inverse is equal to 1. It's a rational number. The cosine of 2 pi over m is rational. That doesn't happen for the other cases, but in that rational case, we get Teichmuller curves. And finally, if we take my favorite billiard table here, the one with type 1119, if I make this length 1 and this length the square root of 3 times y, let me call that table QY. So QY has optimal billiards for any y irrational such that y satisfies a certain quadratic equation, namely y squared plus 3c plus 1, y plus c is equal to 0 for some rational number c. OK, so I'm 1 minute over, so I'll take 1 more minute to compensate for the minute I'm over. I just want to say that what I find most remarkable about this development is the following. At first blush, it looks very special. It looks like, OK, so you have 6 cases, and they do these extraordinary things, but aren't they sort of like the exceptional Coxeter groups or something like that? But in fact, this discussion encompasses all of the other discussions that I put on the board today. So for example, if you were to start with the quadrilateral type 1, 2, 2, 3, what does this look like? Here is equal to 4. The angles are all multiples of 45 degrees. It looks like this, sort of a trapezoid. Well, if you reflect this across this edge, you get a symmetric L-shaped table. So it turns out that for this value of A, the corresponding set of forms is the space of forms of genus 2 with a double 0. So in some sense, all we're finding are higher genus generalizations of the stratum of forms of genus 2 with a double 0. And just as in that locus, in that stratum, we could construct the Weierstrass curves, in these higher dimensional strata, we can construct these other new Teichmuller curves. So really, the case of genus 4 is hidden here. The case of genus 2 is hidden here. And in fact, the prim cases of genus 3 and 4 are also hidden in this discussion. And in fact, the same discussion doesn't depend too much on it being a quadrilateral. And the case 1, 1, m minus 2 covers the Veitch case. And the case 1, 1, 1, 2, m minus 3 covers the Ward case. So really, the only thing that's missing from this discussion are the Baumüller curves. And there's an explanation of them as well, but I won't try to go into it at this point. So one last word. Let me just anticipate a question. What about pentagons? Well, of course, we investigated it with a fairly narrow focus when the exact constructions we were using would give something interesting for higher, for polygons with more sides. And they didn't. They gave something, but it was always an existing stratum. So it wasn't, we didn't get new primitive examples, except we missed one case, which is 1, 1, 2, 2, 12. And this pentagon is very beautiful. It's related to this quadrilateral, which I haven't drawn yet. This is the 1, 1, 2, 8 quadrilateral. And this gives a 4-dimensional subset of invariant forms. If you let this edge go out like this, that defines a family of pentagons, and that gives a 6-dimensional family of invariant forms that was previously unknown. So the fact that such a simple extension of an arc can lead to a previously unknown invariant subvariety really leads me to conclude that we're still in the age of discovery.
Who's the result?
Thank you. Sorry?
Who's the author?